All right, so section 11.3 is going to get us thinking about derivatives. And the specific type of derivative we're going to talk about is called a partial derivative. And so I think this is really the start of calculus for us in this class, and I think a lot of you are really going to enjoy it. But the idea behind a partial derivative is that we've been thinking about multivariable functions. Like z equal to f of xy, or even you could think about some function g that depends on x, y, and z. Usually we would set that equal to some number when we are trying to plot things. And if we want to take derivatives, they're also going to depend on many variables. So just to get us thinking about this, I'm going to draw a quick little picture. So let's think about some z equal to f of xy that gives us one of these bowl shapes. Those are kind of fun to think about. And let's compare it to before when you would plot in x and y. Here's like a curve. And I'll use g of x just because I used f over there. So from your first calculus class, you should be able to kind of, I don't know. Actually, this is more like that, for example, is what I've drawn here. And you know how to take a derivative of this y, just using like the power rule. And you know that when you look at this curve, your derivative is kind of telling you the slope of the tangent line. And so you have a good feeling for derivatives with respect to one variable. But once we go to two variables, if you hold on to, we're looking at a picture of a curve here. So your graphical feeling about what a derivative is. This is also I'm trying to show you kind of like the shape I drew, because I know my shapes aren't very good. But the graphical interpretation of a derivative you have is that it's the slope of a tangent line. So if I kind of pick a point on my curve, I could imagine, okay, there's a slope that kind of goes that way running down the side of the upside down bowl. But also maybe I could imagine that there's a slope this way going down the side of the bowl that's kind of facing us. And you could imagine that this is kind of running in the x direction and this is kind of running in the y direction. And both those tangent directions make sense with what we know of derivatives, but it just depends on where on the surface we're looking at them. And so what we're going to find is that sort of this rate of change, this slope, depended on moving forward in the x direction and seeing how y changed. Now with z depending on x and y, we can move forward in the y direction and z changes this way, or we can move forward in the x direction and z changes this way. And so what we're seeing here is that there's more than one way for z to change. Derivatives tell us about rates of change, so there's going to be more than one way to define a derivative of z. Specifically, we'll be able to define it in terms of x or y. So what we're going to do is we're going to think about derivatives with respect to different variables. So just to think about this in terms of what's familiar to you already, when you have y equal to minus x squared, you know how to write y prime of x or dy dx. And you would just get minus 2x when you calculate it. And this is the derivative of y. That's what you would have called it before, because we never really needed to specify that it was with respect to x. But that is what we were doing. We were talking about how y changes with x. When you look at this little slope, it's telling you how much increase in y you get for every increase sideways in x. And so now what we're going to have is we're going to have derivatives of z with respect to x. But we can also compute it with respect to y. Let me give myself a little bit more space there, sorry. Okay. So because z depended on x and y, we can define derivatives in terms of x or y. And I just want to be real clear that this funky looking D was intentional. So this like a floppy or soft-sided D is different from the D you used before because it tells us that you picked a specific derivative, but there was more than one that you could choose from. So that's just a special notation we use here. We could also write f sub x, f sub y, and those are derivatives of f with respect to x or y. And so going back to this picture, that was your y prime of x0, but now these arrows I've drawn right here, this would be d z dy or f sub y. And this other one that went in the x direction would be dz dx or f sub x. I'm going to move that over. It's hard to see. There. I'm specifically talking about these little arrows where I said this one goes in the direction y changes, this goes in the direction x changes. And all this has just been getting you used to the notation that you're going to see. Do I have enough time? I do. Okay. Real quick, I also want to expand this notation for multiple derivatives, and then we'll go ahead and start doing lots of examples. So you know how to take y prime of x, y double prime of x, so on and so forth. Or here's your second derivative of y with respect to x. Now, for our z equal to f of xy, we're going to have d2z over dx squared and d2z over dy squared, second derivatives like you're used to. And then using that second notation, you could write this f sub xx or f sub yy. These mean the same thing, whichever one you prefer is okay. But then we're also going to be able to combine different derivatives. So I could take a second derivative of z, but I could take it with respect to y first and then with respect to x. And the opposite, d2z over dy dx, or f sub xy, is derivative with y. Sorry, derivative with x, then with y. And you could go even higher than this, third derivatives, so on and so forth, following these same rules. I just really want you to pay attention here to these mixed derivatives, in that the ordering is different whether you choose to use the f notation or the partial symbol notation that looks like a fraction. Again, either notation is fine. They're interchangeable. Just calculus was invented by two different people concurrently, and so there are two different conventions for how we show this. And this swapping of order can confuse some students. Most of the time, for really nice functions, which is most functions you work with, it actually won't matter what order you take the derivatives in. But if it ever does matter, you need to make sure you understand what people are saying to do first and then second, or first and then second. So just make careful note of this so that you don't ever make that mistake.